Welcome back to the third part of this video. By now you know what the data structures are and why they matter, but data structures alone are not enough. We need algorithms to operate them. In this video we will define what an algorithm is and list the 6 properties of a good algorithm and classify data structures into linear versus non-linear and go deep dive into static versus dynamic distinction with the real world examples. So let's look at what is an algorithm. An algorithm is a step-by-step procedure for solving a problem, but not every set of steps is a good algorithm. A good algorithm has 6 properties. Let me explain each one of with example. First property is clear and unambiguous. Each step must be precise and easy to understand. For example, add a little salt is ambiguous. How much is a little. Instead add 2 grams of salt is clear. In programming, you should never leave room for interpretation. The second property is well-defined input. An algorithm can take 0 or more inputs. A greeting algorithm might take a name as input. An algorithm that generates a random number might take no inputs, but if it expects a certain type, that must be specified. The third property is well-defined outputs. Every algorithm must produce 1 or more outputs. If you write steps that do something but never return a result, it's not useful. The output could be a number, a message, or a change in state, but there must be something observable. The fourth property is finiteness. The algorithm must terminate after a finite number of steps. Infinite loops are not allowed. Even a loop that runs for 1,000,000 years is technically finite but practically useless. We cannot terminate. If we want, we won't terminate in reasonable time. The fifth property is feasible. The algorithm must be possible with available resources. An algorithm that requires 1 terabyte of RAM on a phone is not feasible. An algorithm that needs a quantum computer is not feasible for most of us. The sixth property is language independent. You can write it in Python, Java, C, C++, or even pseudocode. The logic does not change. That's why we often describe algorithm in plain English or diagrams before coding. Let me give a simple algorithm example making a cup of coffee. So the inputs must be water, coffee grounds, and cup, spoon. First we will boil water, then add 2 tablespoons of coffee grounds to the cup, and then we add hot water into the cup and we stir with spoon and add sugar or milk. Finally, the output is the cup of coffee. Is it clear? Yes, right? Finite and also feasible. That's an algorithm. Now we look at the type of data structures. There are two main ways to categorize them. First, by arrangement, linear versus non-linear. Linear data structures, elements in here, elements are arranged in sequential order. As you can see in the diagram also, each element except the first and last has exactly one predecessor and one successor. Think of a line of people waiting for a bus. Examples like array, linked list, stack queues, which will be detailedly discussed in later sections. In an array, the element at the index 5 has a predecessor at index 4 and a successor at index 6. Non-linear data structures. Elements are not arranged in a linear order. The element can have multiple predecessors or multiple successors. Examples like a tree. Think of example like a family tree. A parent has multiple children. And a graph, like a social network. Person can have many friends and friends with many others. We can also classify data structures into static versus dynamic. Static data structures, memory is allocated at compile time. The maximum size is fixed and cannot change during program execution. Examples include arrays declared with a constant size. Access is very fast because the computer knows what exactly where each element is, but the insertion and deletion are slow because you may need to shift many elements. In dynamic data structures, memory is allocated at runtime. The size can grow and shrink as needed. Examples will include linked lists, dynamic arrays. Insertion and deletion are fast, but access is slow because you often have to traverse from the beginning. The static versus dynamic data structures. Imagine a parking lot with exactly 100 spots like these, numbered from 1 to 100. If you want to park in spot like 42, you drive directly there, which has constant time, no searching. That's the advantages of arrays, extremely fast random access. Now if you want to add a new car between 42 and spot 43, you can't. All spots are fixed. To make room, you would have to move every car from spot 43 onward one spot to the right. That becomes very slow. Similarly, detecting a car from the middle requires shifting. Arrays are good when you are mostly read data by position and rarely insert or delete in the middle. Dynamic data structures. Dynamic data structure is like a treasure hunt. Each clue tells you where the next clue. For example, clue 1 say go to the tree. Clue 2 say go to the rock. Clue 3 say go to the fountain. Likewise, you will point to the next. So, the deletion is similarly fast. However, to find clue number 42, you must start at clue number 1, follow the arrow to clue 2, then clue 3, and so on until you have followed 41 rows to find the clue number 42. So linked lists are good when you are frequently insert and delete in the middle. and rarely need to access by position. So we will discuss linked list in later sections very deeply. Let me give you real world software examples. When to use array. So remember, there's no single best data structure. You choose based on operations you need most often.